I'll record it, so just in case you need it, okay?
Mhm.
Now, you can see that
And so like
the current has been flipped, right? The
Mhm.
current has been flipped. Because if it is connected to this part here, it's
Mhm.
forward, this is into the page, this is out of the page, there's no current here, but now current here is still the same as this one here.
Mhm.
This bit is connected to that one. This bit is connected to that one. So that's why current has been flipped. Now this will experience force where? Downward, right? This will experience force upward, just like this one here. So as it rotates, the current flips, and that allows this thing to rotate in one particular direction, not like this one, not like this, but keep on rotating. Okay. So if I can just summarize it here, the split ring allows current within motor to flip and thus maintain constant torque. Otherwise, if there is no split ring, motor cannot function because it's not going to rotate constantly. So you can see that this part here was moving down, this part is moving up. But then when this blue part, by the time the blue part arrives over here, it should not have force upward, but has to have force downward. You see that?
Yeah.
That's the reason. Now, moving on to generators. Anyway, force acting on a single part of this wire. So there is force here and here. That's BIL, BIL. There is no force on this part here and this part here when it's flat.
Yeah.
Even if there is, they cancel each other out. So you just need to ignore that. Okay.
Yeah.
Now, when it comes to generators, of course, we have the setting is like this. You have a magnetic field like this, north and south. Very simple. And you simply have this coil again. However, this may be made up of a split ring, same as motors. And you don't need to have any battery, of course, because you're going to rotate it yourself. You can rotate it by your hand, like that. Okay.
Yeah.
Then what it does, it creates its own electricity here. And you can have some kind of a voltmeter or ammeter, right? Maybe you can have an ammeter or something known as galvanometer. Galvanometer. So what that does is just measures how much electricity is generated, that's all. So you may have that sort of situation. In that case, just need to know that as coil is rotated, just as we saw in this case, if it is to move in one constant direction, either clockwise or anti-clockwise, the current within the coil has to flip every time.
Yeah.
So as the coil is rotated, current within the coil flips. So it can go forward, backward, it flips as it rotates. The split ring allows DC, allows because of the split ring there, within the circuit allows a direct current, which means only having one direction, within the circuit. So this is circuit here, within the circuit. So the electricity is generated here, and it's flipping. It's always flipping. But you have the split ring here, which filters out, so which allows only one current. So when this is by the time it flips, it's actually over here. So it only maintains constant current within this one, within the circuit. So it doesn't flip within here. Now, you may have slip ring. Have you heard of slip ring as well? Not sure if you've done slip ring. So you may have a slip ring. So it's just like a circle here, and you have another one. It's a slip ring. So this slip ring, however, slip ring with a lot of summary, and then we're going to move on to question. Okay. So the same thing. So as the coil is rotated, current flips within the coil. So this is coil here, or sometimes known as armature. And within the circuit, it's if we have a split ring, it's constant direction, one direction, one particular direction. But if you have slip ring, flipping effect is not canceled. Okay, so slip ring means one part of coil is always connected to the same point. So this point is always connected to that. This point is always connected to that. Whereas in this case, this point could be connected to this, or could be connected to that. Okay, so that point there could be connected to this or this. So in this case, it only so that point is only connected to that. So therefore, this only allows this makes the current to flip. Okay.
Yeah.
Current generated is AC. So you don't have to understand, I think, for your test how exactly all of these work, but you need to memorize this and this. That if you have a split ring, then you can generate AC, alternating current. If you have a split ring, you can have DC. Okay. Now moving on to this one here. Okay. There's a lot of stuff.
It's just like a brief, the electromagnetic waves. What were they again?
Okay. There's magnetic braking.
Magnetic waves.
Okay.
Because I can do all the questions with the equations, I'm pretty sure.
Yeah, well, I'm just going to cover all these concepts because I think it's necessary. Okay. So that's that sheet. So yeah, so you want to try this one as well?
They're more, that's just general information.
Yeah. So we can maybe start from here. So number 3, A, B, C, and then this is C as well, D, right? Okay.
Mm-hmm.
So you know what flux is, right? So you can think of flux as the amount of field lines. So you can think of flux as number of magnetic field lines through a plane. So plane is usually just a coil. So like if you have a coil and you have this area, so that's area A. So if you have like a magnetic field here, another magnetic S here, N here, and you have these field lines, right?
Yeah.
And if you have this area a bit like this, then at the moment there are 1, 2, 3, 4 field lines, true?
Mm-hmm.
Now, if your area is flat, like this, and then you have a flat area, then you can see there are not many field lines going through, but none of them are going through that plane, true?
Yeah.
In that case, it's 0.
Okay.
So that's why there is cosine theta. So if the magnetic field is, let's say, 5 Tesla, that's the unit of magnetic field. And let's say this is 4 centimeter by 10 centimeter. And let's say this is perpendicular. Then how much is the flux? Flux is given by B times by A. And in this, if it's perpendicular, then the angle is 0. Cosine 0 is 1, isn't it?
Oh, yeah. 1, okay.
Yeah, so what is this angle? This angle, theta, is the angle between the field line and the normal of the plane. So you can see that if you have like a plane like this is the plane, then the normal, this is the normal of the plane, isn't it? And the field lines are going like this. So what's the angle between these field lines and this normal?
It's still 0, yeah.
It's 0, isn't it? That's why you simply multiply the magnetic field by the area, and this will be 1, cosine 1, right? So the answer for this one is, so this is 40 centimeter, so this is 0.04, this is 0.1, so the magnetic field is 5 times by area is 0.004. So you get 0.02, and this is Tesla meter square. That's how you calculate flux. Okay. Now, if your field lines are like this, and you have area kind of like that, flat, then there are no field lines going through this one. And you see the normal of this is making 90 degrees with the field lines, sure? So in that case, flux is B times by A times by cosine 90. So it doesn't matter what these are. Cosine 90 is 0, so 0 times by anything is 0. So 0. So there's no flux.
Yeah.
So you can sort of think of,
that makes sense.
So you can just think of flux as number of field lines going through a plane. If you have 0 field line going through the plane, then the flux is 0. All right. Now, next part is, it's about electromagnetic induction. So this is generation of electricity. So this is the principle behind generator. So what is this? Is a process where a conductor placed in a changing magnetic field causes the production of voltage across conductor. This is okay, prescription, but better way of studying it is, you know what differentiation is, right? This is like differentiation. Differentiation is change in something. It's gradient, isn't it?
Yeah.
So, what this is that as long as you change flux, so change in magnetic flux leads to voltage. Voltage is also known as EMF, electromotive force. It's not actually force, so this is just another name. That's why it gets the name E there, but this is the same thing as voltage. Voltage is given negative of change in flux. So this can be also written as D of phi, D of T, differentiation of the flux. If you take differentiation of this, you get the voltage. All right?
Yeah.
N is there simply because this is number of coils.
Yeah.
So what that means is that if you have, instead of just one coil, you have a number of coils wrapped around like this.
Yeah.
That's the N. That's the number of coils. This is change in flux. This expression is flux, isn't it? Because it's just that one there. And that's change in time. So I'll give you some question here. What I'm going to do is I've got a just very simple question. So this one is within, what's the flux here? So we calculated this before, 0.02, right? So this happened within the magnetic field. So this is North Pole, South Pole. Magnetic field was 5 Tesla. Area was 0.04, was it? 0.04? 0.004. 0.004. So that's why the flux is that, okay? Now, it used to be like that, but I'm going to flip this one by hand. I'm going to suddenly change this orientation so that it's now flat. Like this. So that no field line goes through it. So this is flux before. Now flux after is how much?
0, isn't it?
0, that's right. So it used to be sort of like this, right? It used to be like that, but then now it's rotated suddenly to make the flux 0. Let's suppose that this happened within 1 second. So what I did was literally, I take this coil, can you see me? And within 1 second, it was like that. And within one second, I rotated like this. 1 second. So how much voltage is generated? Very simple. Voltage is equal to minus change flux over change in time. Negative of change in flux, final minus initial, that's equal to 0 minus 0.02 divided by 1 second. Pretty simple, right? So this is 0.02 divided by 1. So therefore, the amount of voltage generated is 0.02 volts.
Yeah, that makes sense.
I want you to try this by flipping this one within 0.01 second. So how much voltage is generated if I do it faster? Do you think will be the same amount of voltage or a bit higher voltage?
I feel like it'd be a little bit higher because you've got 0.02 divided by 0.01.
That's right, 0.02 divided by 0.01, which is 2 volts, right? So if you do that in...
So it's quite a lot bigger.
Yeah, it's quite a lot bigger. It's 2 volts. So that's the meaning of that equation there. Yeah, so what's the relationship between change in flux and EMF, Lizzie?
It's that The
Okay, the clue is right over here.
leads to voltage, so it's a differentiation version, isn't it?
So change. What's the relationship between change in flux and EMF?
Change in flux is equal to
So
volt.
what was flux again, Lizzie?
It
In more understandable everyday term, what was flux? You can think of
it's
flux as,
voltage.
I don't
Oh
know.
no, it's the amount of magnetic field lines through a plane.
That's right. Amount of field lines going through area, right? A plane.
Mm-hmm.
But
And
if
EMF.
so, you can change the flux by
Mm-hmm.
in two different ways. You can either change the area or you can change the magnetic field.
Mm-hmm.
If you increase the area
Mm-hmm.
or you decrease the area or you
Yeah.
rotate the area, that leads to change in flux, right? Or
Yeah.
you can make the magnetic field a bit stronger or a bit weaker.
Mm-hmm.
So
Yeah.
that's how you change flux. And
Mm-hmm.
whenever you change flux, that is going to lead to voltage.
Mm-hmm.
Remember that. Whenever you
Mm-hmm.
change flux, it creates electricity.
Mm-hmm.
Voltage means electricity there.
Yeah.
Now, I'm going to give you another case. So if I just have magnetic field and just have so really strong magnetic field, okay, like really strong, and
Yeah.
I have little section of coil here and it's just sitting
Mm-hmm.
there. Would
Yeah.
there be any electricity produced within that coil? It's
There
just sitting
should
there.
be.
The answer is no.
Is the magnetic field passing over the coil?
Okay, I'm going to draw the picture a bit like this. So let's say you have really strong magnetic field and there is this area and flux. Let's say flux is, let's say 110 million Tesla
Yeah.
meter square. So that's huge amount of field lines going through this area.
Yeah. Okay.
And this is just sitting inside the magnetic field. So would that create any electricity?
If it's not moving, no.
If it's not moving, no. Even if the flux is huge, flux does not lead to electricity. Change in flux leads to electricity, understand? It needs to change. So it needs to rotate. Or the magnetic field must get stronger or weaker. It doesn't matter whether it gets weaker or stronger. Okay, as long as it's changing, then that leads to electricity. Understand?
Yeah.
So that's the relationship between flux and EMF. Now, Lenz's law is about. So we understand that whenever you change in flux, so change in flux is like this. Change in flux is d by dt. That's a change in flux. Just as like velocity, change in displacement of a change in time is velocity. Change in flux of a change, that's the change in flux. This leads to voltage, but there must be a negative sign there. Okay. Now, so we understand that change in flux leads to some creation of voltage, but the question is, what is going to be the direction of the induced current? So we created current, we created voltage, but where is it going to go? The Lenz's law says that it's always going to be in a direction that opposes something. Okay? So it's a little bit tricky. Now, I'll give you a simple explanation. Let's say you have a area here, okay? So this is conductor. This is conductor, like just maybe a copper wire. And let's say you have some bar magnet here, north and south. So this bar
Yeah.
magnet has a magnetic field going like this.
Mm-hmm. Yeah. Yeah.
You know, it's the field line is going like that, you know?
Mm-hmm.
And of course it
And when it
curls around to south
mm-hmm.
like this.
Yeah.
So this is the situation. So there are certain number of field lines going through this circle. This is conductor.
Yeah.
Of
Mm-hmm.
course, this wire, I mean this bar magnet, if it just sits there, it's not going to create any current.
Yeah.
But if you push it in or pull it
Mm-hmm.
out, that's going to change number of flux field lines, right?
Mm-hmm. And the north and south swaps, doesn't it? Once it's in the current?
No. This one doesn't change. This one is constant.
Mm-hmm.
But then when you push it in, some current will be produced here, either clockwise or anti-clockwise, right?
Yeah.
But what is going to be the direction, though? That's a difficult question, isn't it?
Mm-hmm.
As I push it in, what's going to happen is that the Lenz's law says this. Lenz's law. So here are two things. Faraday's law is about the generation of current or induction. Induction means you generate current. So Faraday's law says if you change flux, that is going to what? If you change flux, what's going to happen?
You're going to change the...
So this is the most important bit that we are talking about here. How do you get electricity? How do you generate electricity?
By
changing,
like flipping.
By changing flux.
Yeah.
Understand? So this formula
here,
here,
which is the flipping.
So you got to repeat this sentence here, okay? Change in flux leads to voltage.
Okay, change in
flux leads to
voltage.
EMF. So maybe I want you to repeat that sentence, okay? So change in flux.
Okay. Change in
induces.
Flux induces EMF.
Yeah. So flux does not induce EMF. Change in flux induces EMF.
Which is voltage.
Which is voltage, that's right. Or current. So that's known as Faraday's law. Understand? You need to really engrave that in your mind. So change in flux. So even if that the idea doesn't fully settle in your mind, so simply just memorizing the sentence like that can really help.
Will help.
Change in flux leads. Change in flux induces EMF. Okay, so that leads to induced EMF or induces EMF. Lenz's law is all about the direction of the induced EMF. So why do we use the term induced? Induced means it's like generated, it's created. It is, so EMF is voltage. Induced EMF is a voltage that is direct result of something. It's created by something. So Faraday's law says what? What does the Faraday's law say?
That change in flux induces EMF, which is voltage.
Right. That's right. How do you change flux though, Lizzie?
You change flux when you add... it's the field lines going through.
Yeah, so how do you change the field lines? There are two ways. What flux is given by? B times by A, right?
Yeah.
So how do you change flux?
Change the area?
Change the area. You can, should you make it larger or smaller?
Larger.
Could be anything. It's all about the change. So it doesn't matter whether
Then
it's going to increase or decrease.
well, you'd change the magnetic field lines, wouldn't you?
You can also change the magnetic field. That's right. You either change that. You can make it stronger or weaker. You can make that larger or smaller. It doesn't matter. Change in flux leads to EMF. Okay, change in flux produces EMF. Now, what does Lenz's law say? Lenz's law says that the direction of the induced EMF will be such that it opposes the motion, opposes the change. So what is that change? It's that change here.
Yeah.
Which created it. Now, so I'm going to just go through this fairly quickly. So you see that this bar magnet here is going down. So that is going to create more field. So there was some field lines that is not really passing through that area. But if you push it down, then it's going to create even more field lines going through this area. So that is change in flux. Now, because there's change in flux, it's going to create induced EMF, either that direction or that direction. We don't know that. But these whatever the induced EMF is going to be in such a way that it opposes the change which created it. Which means, so what is that change that created that induced EMF? That is this very motion of pulling this bar magnet down. Which means this whole circuit has to act as if it is North Pole and South Pole. Maybe this is what you were talking about before.
Yeah, this is what I was talking about.
Yeah. So if you have North Pole and North Pole, you see how they repel each other so that it's actually opposing this bar magnet from coming down any further. That means you using your thumb rule, okay? You need to know that if you use your right thumb rule, like this, this is
current.
This is current. This is magnetic field, right?
Yeah.
But there is another thumb rule. It could be actually the other way around. It could be that's the magnetic field. This is the North Pole. And and these curls are current, understand? So your thumb, so this is another version, which is used in induction. If your thumb is North Pole, over here is going to be the South Pole, right?
Yeah.
And that's what this coil is going to act. So this coil is going to act like it is a North Pole, South Pole. So it's like that. That means the current is actually going that way and that way.
Yeah.
So when the current is going that way, then it'll act as if it's a bar magnet with a North Pole and South Pole there.
Okay.
So that's the Lenz's law. Lenz's law is all about the direction of the induced EMF. Moving on to magnetic braking, eddy current. There is AC generator. There's a few other things there. Let's go through some questions. Okay, so you wanted to go through this one, right?
Yeah.
Okay, so is this a motor or generator?
It doesn't say.
Motor. Yeah, I think it's a motor because force is generated. If force is generated, it's a motor. If electricity is generated, that's a generator. Yeah. Do you have some other sheets about the induction?
Not on me at the moment. I'm just kind of trying to learn all the content today,
Okay.
mainly.
So maybe shall we do this one next time and just go through the contents today?
Yeah, sure.
Okay.
Mm-hmm.
Yeah. So there's a bit more contents here. So I'm going to go a little bit quickly, okay?
Mm-hmm.
You can go through the
Yeah,
recording.
I know most of it. It's just, I think, yeah.
Okay. Now, I'm going to talk about magnetic braking and eddy current. So if you have a wheel, so the wheel is just a metallic plate, isn't it? Now, if you apply like North Pole here and South Pole on the other end, so that the magnetic field is penetrating this this wheel. So this is a wheel,
Yeah.
and only like a small section of this is being affected by this magnetic field. Okay.
Yeah.
So there's a flux over here, obviously, right? This is flux. But you can see that this area was within the magnetic field, but then it will, let's say this wheel is going forward, so it's actually going that way. So this section of the area will go forward. So flux wasn't zero. Now the flux is zero, isn't it? So flux wasn't zero, flux is zero.
And now it is.
Now it's zero. So this is change in flux, isn't it?
So
change in flux leads to
EMF.
EMF, which means you see
voltage and current.
Yeah, which is voltage. So this is a metallic plate. So it's not a circuit. So it is a metal plate, and what's going to happen is there's going to be some sort of electrical flow within this area. So that's known as eddy current. Eddy current is induced EMF, or induced current, I would say. It's because it's a current. So you need to know that, when you have a V equals to IR, maybe you've seen this equation before. That's voltage, that's current, that's resistance. If you have voltage, of course, there is current. And this is current. So if there is induced EMF, there's also induced current as well.
Yeah.
So eddy current is simply induced current within, not on a circuit, which is made up of wires, but on metallic plate. Like this one.
Yeah.
So you change flux and it leads to EMF, but because of the Lenz's law, you see, this forward motion of the wheel is responsible for the change in flux, which creates the eddy current. So the direction of the, I'm going to actually write it down here, okay? So Lenz's law, can you see this writing? Says whatever the current created will have a direction which always opposes any change which is responsible for its creation. Okay? The forward motion, the rotating motion of the wheel within the magnetic field causes change in flux, which causes induced EMF, which is also which is the eddy current. Right? This eddy current, according to Lenz's law, must have a direction, must be in a direction which creates magnetic field, which opposes the forward, the original rotating motion of the wheel, because the rotating motion of the wheel creates this eddy current, right? This eddy current must be in a direction which opposes it opposes its creator. So so the eddy current applies opposite force to slow down the wheel. Okay, so that's the end of that section there. Is that a bit too hard, or?
No, I think that made sense.
Okay. Just like this one here, like when you push it down, current is created, which makes this current act as if it's a North Pole, South Pole, and that opposes this very motion of this bar magnet. So it hates its creator. That's the idea. Doesn't want to be created, so it opposes. So this pretty much summarizes. Let me know if you want to know more about this one. Now so we've done magnetic braking. So this is how it's done. You have a metallic wheel, and you simply apply strong magnet on the wheel, North Pole, South Pole, and what it does is it slows the wheel because of the lens.
Yeah. That makes sense.
So we talked about transformers last time, right?
Yeah, already.
So,
and also the generators, we also did all that.
So transformer is made up of primary core. So you have some iron core here like this.
Yeah, I know this one pretty well. And isn't it like the thicker the iron, the like outside, it's actually stronger.
Yeah, that's right. So you have some coil wrapped around here, and you have secondary coil here. The more number of turns you have, so if this is like 100, let's say n equals to 10. Let's say actually 25, whatever, and this is voltage here is, let's say 25 volts, or let's say 50 volts, let's say. Then what's going to be the voltage here? Well, you can simply use that equation. Primary voltage is 50 there. We want to know Vs. Number of turns here is 25. That's 100. So Vs is equal to, that's quarter of, that's 50 divided by 4, which is equal to 112.5, you know?
Yeah, that makes sense.
That's 12.5 volts. Well, what's going to be the current? What's going to be the current here? We can simply use that equation with this equation. Or you can use that equation and that equation, but we don't know how much the current is. So current for one of them must be given. Let's say this is a 1 amp.
Yeah.
Or maybe, let's say 5 amp. No, I'm going to make it 20 amp, sorry. So let's say it's 20 amps. So how do you figure out the current over here? Okay.
You just plug.
Yeah, just plug it in. So we know that secondary voltage is 12.5 volts. Primary voltage is 50 volts. So that
times by
that, right? That's IS here.
Yeah.
And the primary is 20 amp. So that with that and that with that, okay? So we can see IS is equal to, this one go down, this one go up, this one go up this way. Then it's a 20 times a 50 divided by 12.5. So that's equal, that's equal 1,000 divided by 12.5, which is. So I hope that makes sense, right?
Yeah, it does very much.
So the most difficult topic from your test is going to be the induction part, motors and induction.
Okay.
Yeah. Other things are a lot easier. Now, so we talked about motors here, right?
Yeah, we got all that. And generators, we talked all about them too.
AC generator.
I get all the equations.
Right.
Yeah.
So now I talked about generator here. So it's the where is it? Yeah. So if you have a generator here, you can have an AC generator by having split ring or slip ring.
Yeah, I got
Which
that.
one? So if you have a split ring, it's DC. If you have a
a slip ring, it's AC.
Slip ring is AC. Now I'm going to tell you about these equations here. Okay. So that's actually quite simple. So electric motor is. So we covered that. That's all good. So there's a force due to electric current through coil. So what was the equation for that? Force on coil. Force is equal to VIL, right?
And you just plug it in. Yeah.
Now, when you generate electricity, I mentioned the AC generator up there. So direction of the force to generate electric current, you just have to keep rotating in one particular direction, and it creates electricity.
Yeah.
Now, you need to know that the voltage is going to be a sinusoidal function. It will go up and down and up and down and up and down like this. That's this equation here. Because it's a cosine function, isn't it?
Yeah.
And the peak is given by, you see, if you have y equals to 3 sine of x, and you have x here, then what is going to be the peak value here?
Well, it'll be.
Would that be 1 or 2 or 3? The equation is y equals to 3 sine of x.
3 sine x.
So what's going to be the peak value here, Lizzie?
3.
3, that's right. So if I've got the voltage equation as this, what's going to be the peak value here?
If it's.
So the voltage
it'll be just 1.
Is 2 pi f n b a, and then cosine of 2 pi f t.
So that's just 1, isn't it?
No, it's all of that value.
Okay, so that's going to be the peak. Okay, yeah, that makes sense.
That's why that's the peak there.
Yeah. Oh, yeah. Okay.
I feel like there must be a plus sign there. You know?
Really?
Yeah. So, yeah, because it's just a positive sign. This is positive value.
Okay.
So I think you need to place an absolute value here because they're talking about the voltage peak. So voltage peak is EMF peak. So this is just one word. It's not like E times by M times by F. It's just EMF. It's simple. If you have that equation, you have to take absolute value. Okay. And there's something called voltage root mean square. You just need to divide that value by square root 2. Then what you get is something like this. That's a little bit lower than the peak. Yeah. And that is the average voltage. This is average voltage.
Yeah, that makes sense.
Yeah. So I think we already did this one, right? Speed of
light.
I
got that.
Okay, now I'm going to give you a question based on this stuff here. It's very simple, actually. It's just you just need to be able to use this equation. That's all. Let's say there's a coil. Let's say this one is 10 centimeter by 10 centimeter. And let's say this magnetic field is North Pole, South Pole, and let's say the magnetic field is 1 Tesla. And this one is being rotated at 40 revolutions let's say 4,000 revolution per minute. It's making 4,000 rotations per minute. So you need to work out the frequency from there. And then you can figure out the peak voltage.
Okay.
Right?
So it'll be...
let's say this one is wrapped around 100 times.
Okay.
100 times.
Is that 17 for the B magnetic
Just
field?
one Tesla.
Oh, okay.
Okay, so the peak voltage is very simple. You just need to do 2 pi FNBA, okay?
Yeah.
2 pi
Yeah, so it's...
F and then 100, right?
Yep.
And then B is 1. And area is 0.1 times by 0.1.
I didn't see it on millimeters.
Yeah, these are in centimeters. So you got to divide that by 100. Frequency is... so because this is a minute, you just have to divide this one by 60. So RPS, revolution per second, is the frequency, isn't it?
Yeah.
So remember that. So if you have a RPM, just divide by 60. That's the frequency. You have this is 4,000 over 60. That's the peak voltage. What that means is
that's what.
for this generator, it doesn't always have to be cosine curve. It could be sine curve as well. It will rotate up and down and up and down and up and down, and that value there is going to be this much. That value is going to be negative of this much. And the average voltage is simply just take the square root of, divide that value by square root 2. That's all. Okay, so we can call it a day here.
Yeah, that makes sense.
Look forward to seeing you next week as well. And I'll give you
thank you very much.
I think you should just focus on today and tomorrow more on your exam that's going to happen on Monday, right?
Yeah.
Yeah, and then I'll see you on Monday.
Yeah.
Yeah, but you can ask more questions on group chat on our messenger here. Okay, I'll see you next
Thank you very much.